Now continue from previous video where we calculated strain in the top reinforced bar ECS, and we found that it's not yielding. It should yield. Now for that case we need to we follow some step. We done step 1, step 2, and we check that strain in the top reinforcement, the compression strain is less than the yield strain. Now in this case we need to increase the dn value. Now we calculate the dn value, which is around 149 millimeter square. That is the value, but they did not work it out because this is not correct dn. The top reinforcement is not at yield. So in that case we need to increase the dn value. So how much we can increase? Just let's say we have 149 millimeter square, which is not correct. We can make it 200 millimeters and see if the condition that force equilibrium is maintained or not. We need to do these procedures again, like calculating the compression strain in the top reinforcement that we calculated here using the same equation, but this time instead of 149 we are substituting 200 millimeters. So 0.03 times dn is 200. Take away dsc 84. dsc we calculated in the last video, that 84 millimeters over dn 200 give us 0.017. Again we calculated the stresses in the top reinforced bar, compression stresses by Young modulus times strain. Young modulus of the steel reinforcement 200,000 times this 0.017, it gives us 336. Compression force in top reinforcement is the area times the stress. Area is 1232. We take it in the last video, 1232 millimeter square times the stress 336 give us 13,952 newtons. Compression force in the concrete above the neutral axis is the stress alpha 2 fc dash times the area gamma dnb. So alpha 2 we calculated 0.802. Alpha 2 we take it 0.802 times fc dash 32 given in the questions. fc dash 32 given in the questions times gamma value 0.89. Gamma value is 0.89. dn is 200, that we just trying it, 200 millimeters, times the b is 350 given in the questions. B is 350 millimeters given in the questions. That simplification gives this Newton. Tension force in the top reinforcement, please note this tension reinforcement is not changing, it's not depend on the dn value. So whatever the tensile reinforcement that we calculated in the previous one, 1808 000 newtons, that is the same thing staying here. I'm just repeating here for completion. So AST is 3616 times the yield strength is 500. Now we need to check the equilibrium. If this force, summation of these three force, compression force positive and tension force negative, this is the compression force in concrete, compressor force in the top steel reinforcement, and this is a tension force in bottom steel reinforcement. So if this force becomes equal to 0, then this trial dn value is correct. If it's not, then we need to try another dn value. Now substitute this value, this compression force 413 compression force and tension force 1808 000, it seems to be not equal to 0. So this dn value is not correct. 149 is not correct, 200 is not correct. Now 149 is not correct, 200 is not 200 is not correct. So we just reduce little bit dn value, but we are not reducing as less than 149. We always keep this value, which is initial calculation. The first one is 149 millimeters and 200 millimeters. There is two range, did not work it out, so we just reduce 175 millimeters, and we repeat the whole process again. Calculation of the strain in the top reinforcement, 0.03 times dn minus dsc on dn, we get 0.016. Now stress is equal to Young modulus times stress, that Young modulus times strain is 0.016 to 320. Compression force in top reinforcement, area times compression stress 1232, we get the area 1232 ASC in the previous videos, and stress is here, that give this big number. Again we calculate the compression force in the concrete, the procedures is just repeating. Tensile force is not changing, we have 1808. Again we are going to check by summating all these three forces. If it is not 0, it's again minus, it's not equal to 0, so 175 is not correct. Now we know that we have at 175 is 1475.1 force. 200 we know that is 248.19 because it's a negative now, so the number should be between 175 and 200. And this 200 we calculated in the just the previous step, where we have this 204,819.2 newtons. Now we do the interpolations, like 200 minus 175, 204,819 minus 14,751.2 equal to this dn value we need to find, x minus 175, and this force should be 0, like whatever the dn value we get, this force should be 0, so 0 minus 1475.1.2. so if you do the calculations, it gives us x equal to 177 millimeters. So we know now 177 millimeters will give the force equal to 0. Now try dn equal to 177 millimeters. Now strain value, so the calculations of these forces become 1.2 10 to the power 3 Newton, which is almost equal to 0. We repeat the whole procedures again, the calculation for 177 millimeter dn. So we take dn equal to 177 millimeters. Now once we know dn, we need to check for ductility and check for fluxor capacity. So ku equal to dn on d, dn is 177 and d is 520. In the first video about these examples, we calculated d values, which is here. D value is 522 millimeters, which is given 0.34, which is less than 0.36, so it is okay. We can also check the ductility by taking the ratio of steel reinforcement and checking against the maximum reinforcement. Now reinforcement is the area of steel reinforcement take away area of compression reinforcement over comp B times T. So area of top reinforcement, tensile reinforcement, AST is 3616 minus area of compression reinforcement 1232 divided by B times D. B is given 350 and D is given taken as 520 millimeters. Then it gives us 0.0131. Now P maximum is 0.32, alpha 2 gamma fc dash fy 0.36, alpha 2 is 0.802, gamma 0.89, that is calculated here, 0.89, fc dash 32 over 500 give us 0.014. so checking given 0.0131 less than 0.016, so ductility is okay. We need to check the minimum fluxor capacity. Minimum fluxor capacity can be checked by calculating the minimum reinforcement, which is 0.20 capital D small d square FCTF over FSY. And now in here we need to calculate this tensile concrete strength 0.6 Fy, which is given in clause 3.1.1, which is given on page number 44, clause 3.1.1. we have this value FCTF is equal to 0.6 FC dash. So that given, we substitute 0.6 times 32. So in here we substitute the value is equal to 0.6 times square root 32, give us 3.39. that's give us 0.0181. so P, which we calculated 0.131, is greater than P minimum, so minimum fluxor capacity is okay. Now finally we can calculate the moment capacity, because the ductility check is okay, minimum fluxor capacity is okay. So that can be done by tension force times D, compression force in concrete times DC, and compression force in top reinforcement times DSC. We calculated T for 177 millimeters. We calculated T 180800 newtons times D 520. D is 520 millimeters times compression force. Compression force for 177 millimeters. 177 millimeters is 1414997.47 and so on, times the DC value. DC value is is we're going to calculate half gamma dn, that is half gamma dn, which is half times 0.89 gamma times dn 177 is 78.77 minus compression force in the top reinforcement, that is force 177, compression force in top reinforcement 394,240 times DSC 84. DSC 84 simplification gives 796 kilonewton meters. So we need to multiply by the capacity factors 0.85, and this capacity factors is given in table 2.2.2 of AS 3600. Now on page number 36 we have with table 2.2.2 we have this for bending we have this 0.85, so that's give us 677 kilonewtons. Now if Ku is greater than 0.36 and the section is not on existing one, then either increase the ASC or increase the depth until Ku gets 0.36. So we always check that Ku value. Thank you.